So, welcome to my virtual office hours. I didn't get any questions on chapter 7.1, so hopefully that's a good sign that people are doing just fine with integration by parts, or maybe it's late in the term and you haven't gotten around to having questions yet. But the two questions I'm going to talk about are 7.2 number 6 and 7.3 number 4. So for 7.2 number 6, this is in the section looking at trig integrals, and so we want to be clever with the types of trig integrals that we do to compute these. For this one, it's like you might want to use a u substitution, but we see that no u substitution will work directly, right? The derivative of tangent is secant squared, and we have a cosine squared instead. So that's something that's not going to work. We're going to have to be clever. My first approach for all of these problems is to try to simplify them. So I'm going to use the fact that tangent is equal to, well, maybe I'll pull the 3 out front just for simplicity. But cosine squared x, tangent is equal to sine squared, or sine over cosine, and so tangent cubed is sine cubed x divided by cosine cubed x dx. And that's nice, because now I have a cosine cubed in the denominator and a cosine squared in the numerator, and two of those will cancel, leaving me with just sine cubed x divided by cosine x dx. And this is a problem that, now that I'm just in terms of sines and cosines, it's something that's easier to look at. Off the top of your head, maybe I'll write this out as scratch work. It would be really nice if my u were equal to sine, because then my du would be equal to cosine of x dx, and I have a cosine of x right here. But the problem is, and this is something that's a really common error, and this is why I want to bring it up, that this cosine of x is in the denominator, and you can't ever have the cosine of x here is not in the denominator, and there's no way to rectify that situation, meaning that I don't have a cosine x dx available to me. I only have like a 1 over cosine x dx. So this guess of a u substitution is not going to work. We're going to have to be more clever, meaning if u can't be sine, it means that u is going to have to be cosine to be able to solve this. And I'll write that to the side, because trying u as sine didn't work. So let's let u equal cosine x. So du is going to be equal to negative sine of x dx. And that means I need to translate all of these terms into cosines. And thankfully we have a way to do that. I'm going to separate this sine cubed into sine squared x times sine of x dx, all divided by cosine of x. And I'm doing this for clarity's sake, because this sine squared x can become 1 minus cosine squared x times sine of x dx, all divided by cosine x. And now this other u substitution that we proposed is one that's going to work. If I let my u equal to cosine, all of my functions in here are cosine except for this one sine term that's in the numerator now. Notice that this is negative, and so when I convert it to u, I'll have to account for that negative sign. This becomes negative 3 times the integral of 1 minus u squared divided by u du. Well, this looks messy. It's not as messy as it looks. I can use just simple arithmetic of fractions to be able to simplify this. Let's see if I run out of space. And this becomes negative 3 times the integral of 1 over u minus u squared over u du. These are just fraction rules. We have a common denominator that's combined. I can separate that, and this simplifies to just being u, right? So maybe I'll continue right here. Hopefully you'll be able to follow along. So this is negative 3 times the integral of 1 over u minus u du. This is easy to integrate. This becomes 1 over u becomes the natural log of u, absolute value u, should be precise, minus integrating u becomes 1/2 u squared plus c. And then in my final step, I'll substitute back in the fact that my u in this case was cosine x, and I get -3 times natural log of cosine x, sorry. I was covering it up. Uh-oh. Hopefully you can read that. Natural log of the absolute value of cosine of x minus 1/2 cosine of x squared plus c. Sorry that got a little cramped at the bottom. Gosh, this focusing isn't working so well. So that's 7.2, number 6. The big takeaways: try to simplify things algebraically if you can. Identify your u and try to find a du, and then use trig identities to be able to change all of your remaining trig elements into your u, leaving one du left over. So the other problem that I want to talk about is 7.3, number 4, and this one is in the section where we're using trigonometric substitutions, thinking about trig identities that can simplify this denominator. I'm one of those people that unfortunately doesn't have all of my trig identities memorized. I know that sine squared x plus cosine squared x equals 1, but that's not the form that we have here. We need to have something squared plus a constant, and that will be something that simplifies. So I'm going to take this identity and I'm going to divide everything by cosine squared. And when I do that, I derive one of the things that I have on the sheet. This gives me tangent squared x plus 1 is equal to secant squared x. And this is the identity that I want to use. How do I know that I want to use this identity? It's because in the denominator here I have a variable squared plus a constant. And this trig identity has a variable squared plus a constant. And then when I take the square root, it's going to give me something nice. But notice that it doesn't exactly match, that if I were to let, maybe I should have thetas here instead. That'd be better. There's thetas instead. Okay. If I were to do a direct substitution and just let x equal tangent theta, that's not going to be good enough because it's only going to be plus 1, and here there's a plus 9. So one way to think about it is by rewriting this integral as the square root of x squared plus 3 squared. And now if I go ahead and let x be equal to 3 tangent theta, notice what happens. So this is my substitution. Let x equal 3 tangents of theta. Then dx in that case is going to be the derivative of 3 tangent theta, and again the derivative of tangent is secant squared. Notice what happens to my integral. So now I have, by substitution, my dx turns, d theta, sorry, this is just sloppiness on my part. The dx turns into 3 secant squared theta d theta in the numerator. In the denominator, my x squared becomes 3 tangents of theta all squared plus 3 squared. And I'm being really explicit in my work here. When I square the 3 tangents of theta, I'm not going to do anything to the numerator yet. This in the denominator becomes 9 times tangent squared plus 9. I can factor a 9 out of each term. Again, not doing anything with the numerator yet. That's just following along. But when I factor that 9 out, it means that I have, maybe I'll rewrite this as 9 times tangent squared theta plus 1. And we know what tangent squared theta plus 1 is. We wrote it over here. That's secant squared. So this is the integral of 3 secant squared theta d theta divided by the square root of 9 is 3. And this tangent squared plus 1 becomes secant squared, but I'm taking the square root of it, so that just becomes secant of theta. And aha! Let's finish this off. Continuing up here, notice that my 3's cancel. That's great. One of my secants cancels, so I'm left with just secant, the integral of secant of theta d theta, which is the same thing as the integral of 1 over cosine of theta d theta. And maybe this is where we have trouble, because this is something that actually is pretty hard to derive, that we would have to do it by parts, and that's something that you might not necessarily want to do. So you can, at this point, look up in your textbook. There's a table that gives you the identity for what 1 over cosine, the integral of secant. This is something that I would either provide the identities for you on the exam, or you would look it up in a table or online, because this is something that I don't necessarily want you to memorize.